So today we're going to talk about this last little section of chapter 3 that's called relative velocities. And so when we say something is relative, you know what that means?
From a point of view.
Yeah, from a point of view. So if we say something is relative, right? If I say something's easy and you don't think it's easy, right? I think it's easy from my point of view because I've done it 20 times, right? This might be your first time doing something that, whereas you don't think it's easy. So when we describe things and when you talk about these things, those are all relative, right? They're relative to your opinion or your viewpoint about it. So when we talk about relative velocities, we're talking about observations that are made relative to a certain point of view, or relative to a certain location, or relative to their relationship between these two items or two things, okay? And relative velocity problems use a lot of examples of, let's say like if you're swimming across a creek that has a current, right? And it's going to push you downstream. You're not trying to swim downstream, but the current's going to push you that way. Those are relative velocities. So if you're trying to swim straight, the person that's standing on the shore is going to see you really swimming at an angle, right? Because that current's going to push you that way. Can you visualize what that's talking about? So that's a lot of examples that we use for relative velocities. So the thing about these problems is that you really have to be clear about what's the goal, what's this person trying to do, and what do they actually look like they're doing, right? Because those are the two different kind of things that we have to look at here, okay? So let's think about two trains that are traveling toward each other at the same speed. Okay, you don't have to write this example down. You can just think about it. Someone that's standing beside the tracks would be able to see that those two trains are traveling at approximately the same velocity, right? They seem to be moving at the same rate, okay? And they seem to be moving toward each other. If I'm standing on one of the trains, that changes my point of view. It changes my perspective. And so if I'm moving toward that train at 80 kilometers per hour, and it's moving toward me at 80 kilometers per hour, how fast does it seem like that train is going? 160, right? It seems like it's coming twice as fast because we're closing in on that distance twice as quickly. Okay, so that changes the whole point of view. Okay, so if you're going 70 miles down the highway, 70 miles an hour, and you come up on somebody going 55, how fast does it feel like they're really going? 15, right? Have you ever experienced that, right? You're driving down the highway, it doesn't feel like you're going 70, right? But when you come up on somebody that's traveling 60 or 55, it feels like they are crawling, right? It feels like they're just going so slow. That all has to do with your relative velocity, because when you're sitting in the car, you don't feel like you're running 70 miles per hour, right? Your car's moving for you, but you're in motion with your vehicle. So you don't feel that sensation quite as much. But you realistically are moving 70 miles an hour as well, okay? So when you come up on that car, it feels like they're only going 15, when you know that they can't possibly be going 15 miles an hour, right? They're going just slower than you are. Okay, so that has to do with relative velocities. It's all about changing the viewpoint. Okay? So when we have same line velocity, like these two problems we talked about, we just do very simple addition or subtraction, right? You guys automatically knew on the train problem that we'd add those velocities together. It seems like we're going twice as fast, right? When we're closing in on that number, you guys knew that it would be going twice as fast. When we're in the same line right in front of each other or behind, we did the subtraction, right? So the same line velocity, relative velocity problems are simple addition or subtraction. Just thinking about what would be the sensation if you were in that situation, basically. Okay? If we aren't looking at same line velocity, if we're not looking at two objects in the straight line path of one another, then we use vector addition to find our relative velocities. And this is a lot of these swimming across a creek, or I don't know, water pushing something, or the wind pushing, if you push or you throw a paper airplane and the wind pushes it one way. Those are examples of relative velocity. Because let's say I tried to throw my paper airplane straight, but the wind pushes it this way. If anyone else is watching, it looks like I threw it at an angle. Right? But that wasn't my goal. That's what happened because of that wind current. Okay? So if we're not in the same line, we're going to use vector addition. So this is, again, goes back to really simple Pythagorean theorem and sine, cosine, tangent. Okay, so the math behind relative velocities is simple. The setting up of the diagrams and all that kind of stuff is where it gets more complex. Okay. So on relative velocities, it's really, really important that you draw the diagram talking about what's the goal, or where are they going to end up, or what are they trying to do. Okay, that part of it is really, really important. Okay, and labeling the resultant vector is going to be the most important thing. Okay, because when we add vectors, we should add them tail to tip to get to the resultant vector. Okay, resultant vector has to be the one that goes from the origin to the tip of the last vector. That's really, really important. Okay, so the resultant vector is what everyone sees. Right, that's what we think is happening. Like in the paper airplane example, when I throw that paper airplane and the wind pushes it, right, someone else sees it going at an angle. That's my resultant vector, right? I throw it straight, the wind pushes it this way, so that's my resultant vector right there. Okay, does that make sense? That's the one that's going at an angle. That's what everyone sees. Okay, let's try some here. You don't have to write the whole thing down, right? You can just draw the diagram. You can just listen along as we go. It doesn't really make a difference. But the boat needs to travel straight across the river. Okay? And your book does this thing where it labels them with two subscripts, boat relative to the water, boat relative to the shore. I don't like that. Okay? I usually don't even include those at all. Okay? So you don't have to do that if you don't want to. I just really try to think more big picture, and I don't need to label them as much as the book thinks I do. The goal here is that the boat needs to travel straight across the river. The current is flowing to the west. They leave the shore at a speed of 1.85 meters per second. What's the actual velocity of the boat? And with what angle did they need to leave the shore? Okay, so can we envision what's happening here? Right? I want to make it straight across from where I started. But if the current's going to push me to the west, I can't just leave straight across. Right? I have to go this way so that the current ends up pushing me back. Does that make sense? Okay? So which is my resultant vector here? Yellow, green, or black? Black. That's my resultant vector. That's my goal, right? That's what I want people to see, is me going straight across the river. I want to end up straight across from where I started. So that's my resultant vector. And we can tell it's our resultant vector because it goes from the origin to the tip of the last vector. Okay? So this says, I have a current flowing 1.2 meters per second west, right? And it's going west. It's not going east. It's going west. I leave the shore at a speed of 1.85. Right? But I don't know what angle he's leaving the shore. I know he's trying to swim 1.85. The current's going to push him back toward his destination. So we need to find this side of our triangle, which tells us how fast is he actually swimming, right? His attempts plus the current is going to give him a final velocity. Okay, then we also need to find what angle he left the shore at. Okay, so Pythagorean theorem here, you need to be careful because you already have your hypotenuse side. Right? Already have your hypotenuse. You need to solve for A or B. So what velocity or what speed does it look like he's swimming at? 1.41, right? So he's trying to swim 1.85, but he's swimming into the east and the current is going to the west, right? That's slowing him down. Does that make sense? So it should make sense. If we're looking on the shore, we look like he's swimming 1.4 meters per second north. But we knew that he really had to leave 1.85 meters per second at what angle? At what? 40.4. Okay? So if we stood on the shore, it looks like he's swimming this. Okay, it looks like he's swimming straight north because he's going at an angle, the current's pushing him back. But we know he's really swimming, right? He left the shore 1.85 meters per second at 40.4 degrees east of north. Okay? Okay, so in this problem, he's going directly north. He's going to let the current push him this way. And then the resultant, or what we would see on the shoreline, is him being pushed more to the west, right? More to that northwest. So for some reason, when we draw like a creek or something like this, which we see examples of this a lot, I just always assume that, north is across the river. So you can always just draw them that way. It's not a big deal. You don't have to talk about which way the river is, situated. Okay, so 1.85 here and 1.2 meters per second west. Okay, so now we find the hypotenuse and we find the angle at which we think he's swimming, okay, or he's getting pushed at least. (33 degrees) what of what? West of north. Very good.